Hey everybody, welcome back. So when you take a sample, a random sample, you're doing that because you're trying to figure out something about the population. But since you took a random sample, there's going to be a bit of randomness built into your sample average. Your sample average is now a random variable. And so we need to, well, we can first of all treat it like any other random variable, so it can have its own distribution and we can talk about its own mean and standard deviation. And the fact that it is a random variable means that we're going to have imprecise estimates about what the population is. And what we're going to discuss today is our first steps towards constructing a confidence interval. And that interval is going to be our way of kind of conveying the imprecision of our estimates. So rather than just saying our best guess is something, we'll start saying things like, well, our best guess is something, but really we're 95% sure it's going to be between these two numbers, and any number inside that range should be considered plausible. So this is just going to be our first step into really understanding confidence intervals. But before we get into actually constructing them, let's review some of those fundamental things that we need in order to do that. So just as a reminder, we want to know something about, let's say, U.S. income. And so every single person in the U.S. is a member of this population. We'll call that X. Now the average income for the U.S. might be some number. We'll call that mu. This is our population. Now we can't sample the entire population, but we can draw a random sample from that population, and from that calculate a particular number, our best guess, our sample average. The thing is, if we had taken a different sample, we would have gotten a slightly different number. So here's our first sample, our second sample, and we could have gotten, well, an infinite number of different samples, really, from this parent population. Now, each particular draw is a realization of some random variable. We can think now of our x bars as themselves random variables. What the central limit theorem tells us is that the distribution of the x bars is centered right over the distribution of x. So in other words, our sample averages are, on average, good estimators of what the population mean is. Now, like any other random variable, it's going to have its own mean and its own standard deviation. The standard deviation, we're actually going to give this guy a slightly different name. We're going to call it a standard error. This guy might be normal mu sigma. And the standard deviation of the x bars is going to be much smaller. And what the central limit theorem also says is that if these numbers here, these sample sizes are large, then this guy will be normal even if the population isn't normal. So we're actually going to leverage this in order to construct a confidence interval. Just to round out our discussion, our review of the central limit theorem, we have that the distribution of this new random variable that we're messing with, it's going to be normal just as long as our sample size is large enough. It's going to be unbiased, so the average of x bar is equal to the average of x, and the standard error is equal to the population standard deviation, but it is divided by the square root of n. So how precise are our estimates? Our estimates, remember, are x bars. You might draw one particular sample and give me one particular estimate, but we could all have different estimates. So how far off can one of these estimates be from the truth? Well, we know on average they're correct, but how different can one particular estimate be? That's really a question about the standard deviation of x bar, or again what we're calling the standard error. So when we're asking how precise are our estimates, really we want to know what determines the size of the standard error. Two things, because the standard error is sigma over the square root of n. So two things determine the size of the standard error. If the underlying population itself has a whole lot of variation, then we're slightly less accurate with our estimates. In other words, if you've got a whole bunch of billionaires, a whole bunch of really poor people, a whole bunch of in between, and you take a sample of 10 people, well, you could have a whole different wide range of different estimates. My sample of 10 could be very different from your sample of 10. Not just because 10 is a small number, but because we're sampling from a population that itself has such wide variation. So our estimates of the average aren't going to be as good. If everyone in the United States had exactly the same income, well then, hey, give me a sample of one person and I know exactly what that income is. So the population standard deviation being large means that our estimates are less precise. It's also the case that our standard error depends on the sample size. The larger our sample size, so the larger n is, the larger the square root of n is. And when this denominator goes up, the whole fraction itself gets smaller. In other words, if you wanted to know what US's income is and you drew a sample of size 10, you'd have some estimate. But if I told you that you estimated a sample from like 10 million people, you'd be I trust the 10 million one more, right? That's a big sample size. Or what if I told you it was 100 million that I sampled? Well, hey, I'm pretty sure whatever number you get, that's going to be a pretty precise number, right? And that's what this thing really says, is that as n increases, the standard error decreases. And so this guy just gets smaller and smaller and it collapses around its own mean. So those two things are going to determine the precision of our estimates. And that is exactly what a confidence interval is supposed to convey, the precision of our estimates. So how do we construct a confidence interval? Well, the first thing we need to lay out before we start constructing anything is, how accurate do you want your interval to be, or how narrow? How confident do you want to be that your interval contains the true number? If you tell me you want to be 100% accurate, well then, all right, if we're doing US income again, I can tell you with 100% accuracy that the interval I'm going to give you contains the true average income for the US. You ready? Negative infinity to positive infinity. 100% chance, whatever the true average income is in the United States, whatever that is, guarantee it's some number between negative and positive infinity. Now, that might be a true statement, but it is not terribly useful at all. So maybe 100% isn't that great. We could do 50%. Right? So that might give me a very narrow interval, but then, well, there's a 50% chance that the truth lies within that interval, and all 50% chance that it's outside of that interval. And 50-50 isn't terribly reassuring either. So some number between 100% and 50% kind of hits that sweet spot where we're fairly confident that the truth lies within that interval, but we're not so confident that that interval becomes unbearably huge so that it's not very useful. Now, you get to decide how confident you want to be. The profession is kind of glommed onto 3 different levels of confidence: 90%, 95%, and 99%. Now, those are arbitrary numbers, but those are the ones that the profession has kind of glommed onto. 90, 95, and 99%. So before you start going and doing any kind of calculating, just decide what level of confidence you want. We're going to use 95%. One, because it's easier. We'll get to use our rule of thumb of 2 standard deviations captures 95%, but also because most of the statistics profession is just glommed onto 95 as the one they use the most. So of those 3, 95 is the most commonly used. So that's our first thing. We need to establish our confidence level. Then we draw a sample of some particular size. We can calculate our own particular sample average. It's one of an infinite number of sample averages that we could have collected. And then we need to know, well, what is the standard deviation of this random variable? Actually, not of this particular random variable, but of all the random variables that we could have chosen. And that's our standard error. Standard error is the population standard deviation, so standard deviation of x's, divided by the square root of the sample size. And if we're not told sigma, then we can approximate that using the sample's standard deviation. So that's the next step, is calculating the standard error. That is, in other words, if we're looking at all the possible x bars, how widely apart is this thing? We want to construct some plus and minus that gives us 95%. And that's indeed our final step. Our confidence interval is going to be our particular sample average plus and minus something. That something, by the way, is called the margin of error. And for a 95% confidence interval, our margin of error is 2 standard errors. 2 because of that rule of thumb that 95% of your observations are plus or minus 2 standard deviations from the mean. So that 2 comes from our rule of thumb. Our standard errors are these guys here. So a confidence interval really just means plugging in some numbers here so that we can get a plus or minus range for the mean. Let's work out some examples just so that we can make this a little bit more concrete. So suppose you took a survey of 1,162 people and asked them what their monthly household income was. Now the average of these particular people turns out it's $1,227 per month. It's quite low. And the population standard deviation, and here I'm just, by the way, just presuming we somehow know the population standard deviation, so sigma, was 575. Let's construct a 95% confidence interval for what the true monthly household income for this particular population is. So let's start with a fresh screen with all of our useful information. Here we've got our sample size, our sample average, the population standard deviation, and now let's calculate the confidence interval. All right, so we can plug in some numbers. Our confidence interval will be x bar plus and minus 2 standard errors. Now what's a standard error? It is sigma over the square root of n. So 575 divided by the square root of n. And we can just plug this into a calculator and see what we get. Okay, so I pulled out my calculator and I got 1227 plus and minus 33.7374. And if we do the plus and minus, that gives us 1193 to 1260.74, or approximately 1193 to 1261. So that's our interval. Now our best guess is still smack dab in the middle. It's still 1227. So right in the middle of these two numbers is 1227. Oops, 1227. And then we just tack on a margin of error, which is 3374. Okay, so it's pretty straightforward. So you might be asking, like, so what's the big deal about this? Why are we going so slowly? Well, it gets more and more complicated whenever you want to do slightly more realistic things. For example, it isn't exactly 2 standard errors, but it's a useful rule of thumb. And I think we've reached a point in the course where now we can be absolutely precise and say it's not exactly 2, it is a number that's very close to 2. We also need to consider, what if we wanted a confidence interval that wasn't 95%? We know that approximately 68% lies within one standard error or one standard deviation, but we don't have a rule of thumb for 90% and 99%, so we need to develop that. We might want to make adjustments for a small sample size, and then we might not actually know what the population standard deviation is. Now, we can use the sample standard deviation as an approximation of that, but that adds a whole nother bit of uncertainty, and we need to accommodate that when we're constructing our confidence intervals. So tune into the next slide deck. We'll start attacking each one of these complications. But for the time being, thanks for your attention, and I'll see you next time.